In this lesson, we look at how computers represent real numbers. We will see how floating point representation uses a sign, an exponent, and a mantissa to store very large, very small, and fractional values. Whole numbers can be represented directly using binary. Negative numbers can be represented using 2's complement. But real numbers are more difficult because they may contain fractional parts. And some real numbers have infinitely many digits. A computer has limited memory, so it cannot store infinitely many digits. Instead, it stores an approximation. The method used is called floating point representation. Floating point representation is based on scientific notation. Let's begin with a decimal example. The number 438.7 in base 10 can be written as 4.387 multiplied by 10 to the power of 2. The value 4.387 contains the significant digits. The exponent 2 tells us how far the decimal point must move. A positive exponent moves the point to the right. A negative exponent moves the point to the left. For example, 0.00625 can be written as 6.25 multiplied by 10 to the power of minus 3. The exponent is negative because the decimal point must move 3 places to the left to recover the original number. Floating point representation uses the same idea in binary. A floating point number has 3 main parts. The first part is the sign bit. The second part is the exponent. The third part is the mantissa. The sign bit tells us whether the number is positive or negative. A sign bit of 0 represents a positive number. A sign bit of 1 represents a negative number. For example, if 2 floating point patterns have the same exponent and mantissa, but different sign bits, then one represents the positive value and the other represents the corresponding negative value. The exponent determines the scale of the number. It tells us how far the binary point must move. The mantissa stores the significant binary digits. The standard commonly used for floating point representation is called IEEE 754. Two common IEEE 754 formats are single precision and double precision. Single precision uses 32 bits. It uses 1 bit for the sign, 8 bits for the exponent, and 23 bits for the mantissa. Double precision uses 64 bits. It uses 1 bit for the sign, 11 bits for the exponent, and 52 bits for the mantissa. Double precision uses more memory, but it gives us greater precision and a larger range. Now let's look at normalization. Suppose we have the binary number 101.101. To normalize it, we move the binary point so that only one non-zero digit remains on the left. This gives 1.01101 multiplied by 2 to the power of 2. The point moved 2 places to the left, so the exponent is 2. Now consider a small binary value, 0.001101. To normalize it, move the binary point 3 places to the right. This gives us 1.101 times 2 to the power of negative 3. The exponent is negative because the original number is smaller than 1. These examples show that the exponent is really a record of how far the point moved during normalization. In a normalized binary number, the leading digit is always 1. Because the leading digit is always 1, the IEEE 754 standard does not store the 1 explicitly. Only the bits after the binary point are stored in the mantissa. For example, in 1.01101, the leading 1 is implicit. The stored mantissa begins with 01101. This gives the computer 1 extra bit of precision without using another physical bit. Now let's look at how the exponent is stored. The exponent must represent both positive and negative powers of 2. However, the exponent field itself is stored as an unsigned binary number. To make this possible, IEEE 754 uses a bias. In single precision, the bias is 127. The stored exponent is found by adding 127 to the actual exponent. Suppose the actual exponent is 3. Then the stored exponent is 3 plus 127, which is equal to 130. The binary representation of 130 is 10000010. Now suppose the actual exponent is negative 4. The stored exponent is negative 4 plus 127 is equal to 123. The binary representation of 123 is 01111011. So both positive and negative exponents can be both stored without using a separate sign bit for the exponent. To recover the actual exponent, we simply subtract the bias. For example, if the stored exponent is 129, then 129 minus 127 is equal to 2. So the actual exponent is 2. If the stored exponent is 124, then 124 minus 127 is equal to negative 3. So the actual exponent is negative 3. Now let's decode a simple floating point value. Suppose the sign is positive. Suppose the actual exponent is 2. Suppose the mantissa represents 1.01 in binary. The binary value 1.01 means 1 plus 1/4, which is equal to 1.25 in decimal. Now apply the exponent. 1.25 multiplied by 2 to the power of 2. Since 2 to the power of 2 is equal to 4, the result is 1.25 multiplied by 4, which is equal to 5. So this floating point value represents positive 5. Now let's try a negative example. Suppose the sign bit is 1. Suppose the actual exponent is 1. And suppose the mantissa represents 1.1 in binary. The binary value 1.1 means 1 plus 1/2, which is equal to 1.5. Now apply the exponent. 1.5 multiplied by 2 to the power of 1 is equal to 3. The sign bit is 1, so the final value is -3. This shows that we can decode the three parts separately. First, determine the sign, then decode the exponent, and finally, interpret the mantissa and apply the exponent. Now let's try to decode a real-world full 32-bit example. Suppose we are given 01, 000001, 00111 followed by 19 zeros. The first bit is the sign bit, which is 0, so the number is positive. The next 8 bits are the exponent. Here, the exponent is 10000010. This is 130 in decimal. So, we subtract the bias, 130 minus 127, which is equal to 3. So the actual exponent is 3. The remaining bits begin with 0111. Because the leading 1 is implicit, the mantissa is 1.0111. Now interpret the mantissa. The 1 before the point contributes 1. The first bit after the point contributes nothing. The next bit contributes 1/4. The next contributes 1/8, and the final one contributes 1/16. So the mantissa is 1 plus 1/4 plus 1/8 plus 1/16. This gives 1.4375. Now let's apply the exponent. 1.4375 multiplied by 2 to the power of 3. Since 2 to the power of 3 is equal to 8, 1.4375 multiplied by 8 is equal to 11.5. So the floating point pattern represents positive 11.5. Now let's look at an encoding example. Suppose we want to represent positive 6.5. First, we convert it to binary. The whole number part, 6, is 110. The fractional part, 0.5, is 0.1. So, 6.5 is 110.1 in binary. Now we normalize it. This becomes 1.101 multiplied by 2 to the power of 2. The sign bit is 0 because this number is positive. The actual exponent is 2. In single precision, the stored exponent is 2 plus 127, which is equal to 129. The binary representation of 129 is 10000001. The mantissa stores the bits after the leading 1, so it begins with 101. The remaining mantissa positions are filled with zeros. So the three fields are: the sign will be a 0, the exponent is 10000001, and the mantissa is 101 followed by 20 zeros. This is how the value 6.5 is divided into the three parts of the floating point representation. Now let's look at precision. Suppose we want to store the decimal value 0.1. In binary, this value does not terminate. Its binary representation continues indefinitely. A computer cannot store an infinite number of bits, so it stores the closest available approximation. This means the stored value is extremely close to 0.1, but not exactly 0.1. This can produce results that seem surprising. For example, a computer may calculate 0.1 plus 0.2 and obtain a value very close to 0.3, but not exactly equal to it internally. This does not mean that the computer added it incorrectly. It means that the original values were already stored as approximations. The same issue occurs in decimal. For example, 1/3 is 0.33333 and so on. If we only store 4 decimal digits, we might store it as 0.3333. Multiplying this approximation by 3 gives 0.9999, which is not exactly 1. The problem comes from limited precision. Floating point representation behaves in the same way, but it uses binary digits. Now let's compare range and precision. The exponent controls the range. A larger exponent allows the computer to represent larger or smaller values. The mantissa controls the precision. More mantissa bits allow the computer to preserve more significant digits. For example, two numbers that are very close together may become indistinguishable if the mantissa is too short. Suppose a system can only store 3 significant decimal digits. The values 1.234 and 1.235 may both be rounded to 1.23. The system then loses the difference between them. Floating point representation faces the same limitation in binary. Now let's look at the difference between overflow and underflow. Overflow occurs when a result is too large for the available exponent range. For example, in double precision, multiplying 10 to the power of 308 times 10 to the power of 308 produces a value that is too large to represent. This result may therefore be stored as positive infinity. Similarly, multiplying a very large negative value may produce negative infinity. Underflow occurs when a non-zero result is too close to 0 for the available exponent range. For example, 10 to the power of negative 300 multiplied by 10 to the power of negative 300 is far smaller than double precision's numbers can normally represent. The result may be rounded to 0. Before reaching 0, IEEE 754 can use subnormal numbers. These represent values smaller than the smallest normalized number, but with reduced precision. The standard also includes NaN, which means not a number. NaN is used when an operation has no meaningful real number result. For example, the square root of -1 is not a real number, so a real floating point calculation may return NaN. Another example is 0 divided by 0, which is undefined and may also produce NaN. Infinity is used for results that exceed the representable range and for some divisions by 0. For example, 1.0 divided by 0.0 may produce positive infinity, while -1.0 divided by 0.0 may produce negative infinity. The intuition behind floating point representation is that a fixed number of bits must represent values across a very large range. Floating point representation allows computers to store and process real numbers using a sign, exponent, and mantissa. Because only a fixed number of bits is available, this representation balances range and precision, which can lead to rounding, overflow, and underflow.